Hello, can you hear me? Okay. Hi, Nishi is here. Oh, okay, yeah. Okay, so we are ready to go. Hi, welcome. Good afternoon, everybody. Thank you for coming. Today, I'd like to talk about power capping applied in Alibaba data center. I'm from Alibaba, responsible for power management optimization for Alibaba Cloud. The first is about our power capping technology, and also the scheduling on racks with flexible power supply, and a summary and a recommendation. And after my presentation, our collaborator, Nishi's team from Intel, will also do another presentation. Okay, this may be a little bit complicated. There's nothing new. Basically, it's based on RAPO, so-called RAPO to do power capping. What we add using our software intelligence is we just do, from our business perspective, we set up several conditions when we want to do power capping. And if you look at the right-hand side, the top 5 reasons why people may want to do power capping. They want to save energy and want to save money. The likelihood for the rack to go above the capacity, actually the likelihood is not so high so far. And secondly, they want to limit power of the data center. That's because in China, maybe the government say, okay, right now this year summer is too hot. Please limit your data center power consumption. That's just simply is the political reason. You have to lower your power consumption. So no excuse. Although your data center overall watermark is not very high, but you have to lower your power consumption. Okay, and then number 3 is our commonly understood reason for the power capping. The power exceeds the rack quota. And also sometimes there may be some cooling facility failure, and then we need to lower the power load. And sometimes for very low chance there is a power supply failure. Okay, and basically we use the CPU RAPO to do power capping. And for the other red lines, I call it a software method. That's because for our customers, they do not want their performance to be negatively impacted. For example, if we lower GPU power, typically they invest a lot on the AI applications. They do want to protect their investment. So when we have to lower power, then we just use CPU to lower CPU first. If CPU load can be lowered, we hope the GPU load and other components load can also be lowered. But we do not lower GPU and other components like FPGA power first. Yeah, for other details, if you are interested, you can contact me. And from this slide, I want to show a case in our real application. This from the application perspective, why we need power capping. In most people understanding, power capping always helps. That means it can avoid service interruption. But in our real scenario, we found it's not always true. Here I show you an example. Say we have 16 instances. You can understand the instance maybe it's a virtual machine or maybe it's a job. I just use instance to refer to that kind of abstract entity of execution. You can see we have 16 instances. They have dependencies. The arrow means after you complete A, you can do B, C, D. And here means dependency. And the 16 instances, they are mapped to 12 nodes on 4 racks. And you can read the wording here. Unfortunately, for some reason, we have to do power capping. And the rack 3, because of maybe very severe power failure, Then rack 3 is put in a fail-safe mode, for example, S5. And rack 4 also, the total power exceeded the capacity. Then the machine on rack 4 is put on 1.2 gigahertz, which is PN, the minimum frequency of the processor. And rack 11 is a little better, and the processor can run 2.0 gigahertz. And the other, they also run 2.0 gigahertz. What happened, unfortunately, if we do power capping, the node J will be gone, because node J, is on rack 3 in the fail-safe mode, right? The node J is gone, and then node K is gone, because node K, the performance too low, and consequently there is an avalanche, and maybe some internal software queues. They maybe just very quickly they filled up, and the service stopped. However, if we do not do power capping, we just shut down the two nodes, J and K, and we replace with new nodes. Maybe there is service, online service, operation and maintenance service. Then we can quickly resume service, and it will service as normal. So this example tells us power capping sometimes may hurt, especially the unexpected performance is not good to the cloud business. So if possible, we want to avoid frequent power capping. Here is another example. To increase the utilization of the rack, we want to increase the watermark of the rack power utilization. Initially, we thought we may map several apps onto a common rack, but we ask each application to assign priority for their servers. Tell us which server of your business is low priority and which are high priority. If you can volunteer part of your servers is low priority, we can give you some discount. However, we found everybody, all the applications, they will say, all my servers are high applications, high priorities. So that means our initial design maybe not so successful. We thought if somebody in low priority server farm, they can use the green. But if there is a conflict, or if the high priority server keep expanding their power consumption, then the low priority server should yield to that high priority servers. However, that doesn't happen. Everybody is high priority server. And then we thought maybe we should create a capability to increase a rack power supply flexibility. Then everybody will be high priority. But in case it exceeds the nominal rack capacity, we have a capability to increase the rack power. The total accommodated rack power can be higher, at least to be higher for a short period of time. If we can have that kind of rack with flexibility power supply, then next control will be on our software side. We can create a scheduler. The scheduler can get some input from global scheduler, and it can detect when I need a higher power supply. And if for example, you have a battery, then the battery can discharge to provide a short-term high power demand supply capability to the server. Then we do not have to do power capping. If the duration of the high utilization doesn't last very long, then it should be fine. Based on the concept, we do collaboration with our one vendors, for server, especially generic server, Intel is only choice, right? So it doesn't mean we have many choices, but Intel right now is the only choice. Then we have collaboration with Intel, and we get a lot of help from Intel. They get the battery and also the discharging technology. And Nishi will show that later. Also, from the software perspective, we want to understand the benefit to use the battery, and also when it does harm and when it can benefit. So in our software, we want to manage timing, but today in implementation, the timing is only managed in the hardware. This in the future, we are going to manage timing, especially when we have a centralized battery farm. In that time, maybe the energy saving can be will make more sense. Here is some details about the algorithm. I do not think I have enough time to go through the details. Basically, it does several condition check. When there is an outage, we are going to use the battery like a traditional UPS, distributed UPS. Otherwise, when the utilization is high, for a short period of time, then we are going to discharge the battery to provide transient high power capability. Okay, so for my part, the summary, we use the battery as a backup source. It can be a traditional distributed UPS, or it can provide a short-time transient performance boost capability. It's nimble, flexible, and also cost-effective deployment. If you consider, we can use cheaper parts powered by battery. Also, we can avoid expensive cloud service shutdown. The cost saving is even more significant. Also, the software coordination, scheduling, and application awareness is the key factor to use the flexibility. Okay, so next one, let's invite Nishi.
Hi, this is Nishi, and I'm a principal engineer with Intel. I'll be talking about what power management capability we are offering our cloud service providers, as well as towards the end, we will have a recorded demo of our smart BBU or a turbo rack that we are also using with our power management capability. Justin covered the rationale why they are doing power capping and power management. We are also getting quite a bit of requests from our customers who are seeing it as a challenge. As you know that there is a disconnect between the rack refresh cycle as well as the server refresh cycle. And since in one rack generation, there can be 3 server generations, and the power and the thermal profile of that can be different. So that results into reducing the rack density of the in a data center, and that impacts the TCO for these customers. We are working quite a bit with the PRC customers and some of the US customers also, who have come to us and says, as we are going from gen to gen, the power density is reducing, how can you help? So some of the capabilities that we have, we are working with them on those. So this data that we have on this slide is from a very large cloud service provider. We worked with them. We collected the power data at a rack level for 6 workloads. We collected that on 30 of their racks for 200 days, and it has about 10 million logs. And what we found out that sometimes we are over-provisioning the rack. Right? So in this particular customer's case, only 1% of the servers were utilizing that 15% of the provision power. So that is an opportunity for this customer to increase the rack density by. So we were able to work with this customer to increase their rack density by 15 to 20%. What we do, the first step, as we said, is we go in and we do the power profiling to understand the opportunity. Is there any opportunity to even improve the track density? And then the second step is, if there is, we work on using some of our control algorithms as well as technologies. And in order to build these technologies, in order to build these algorithms, we start with the basic telemetry that is available on our platforms. We use Node Manager as well as Intel Xeon Scalable Processor. We tap into the power telemetry, which is your system level telemetry, as well as the component level power information. We tap into the thermal telemetry, which is your inlet, outlet, and volumetric airflow. We tap into the utilization information and the power limiting capabilities of Node Manager, power limiting at the boot time as well as the runtime. So those are the basic ingredients that we are monitoring to work with our control algorithms. So how do we, what are the key features or options in this technology? The first one is static capping. When we work with customers, we are looking at both options, which is static capping and dynamic. In the case of static capping, we are capping each individual server at a different power profile so that it doesn't violate the power budget. But in some cases where we have seen static power capping can result into performance degradation. So that's why we are working with another technology, which is dynamic power capping. So you are capping or allocating power to the servers in the rack based on the demand and based on available power capacity. That's another one. The third one is the dynamic rack power provisioning, where for the peak demands, we use smart BBU, and we will have a demo for that. So as there are peaks, and we observed with this customer, there are only peak periods anywhere from 3 seconds to maximum of 5 minutes, and we can use those smart BBU for that purpose. Then we are also, so the first 3 options we have already deployed with some of our customers. The fourth option is where it is intelligent power-aware scheduling. That is something we are right now working on. It is basically depending on your power-aware or depending on your power telemetry, you're making intelligent decisions within the rack. So moving workloads around to meet that power budget demand, power budget profile. And then the other one is dynamic cluster performance management, where you're adjusting the performance states based on the power demands as well as the resource utilization. So these are some of the options we are working on. What were we able to do with this cloud service provider? As we discussed earlier, that we saw that these racks were over-provisioned. So we were able to minimize that margin. That's number one. Number two, we were able to increase the peak capacity. And number three, we were able to use the smart BBUs for those peak demands. And we were able to get this customer to a density improvement by 20%. So if you look at before and after scenario, group level power capping helps with protecting the battery and the rack power, whereas using the battery backup handles those peak powers. So what do we offer Intel, as an Intel? We have software or the intelligence. We have real-time power analysis that we perform to understand those opportunities. We offer algorithms which are doing power capping and dynamic peak capacity provisioning, as well as intelligent workload scheduling and migrations. We are also contributing to Redfish APIs so that this can easily be integrated into any applications. On the firmware side, we have 2 algorithms. One is adaptive power rebalancing algorithm, and the other is configurable power limiting algorithm. And then the hardware piece is also very unified architecture, which supports both OCP as well as conventional racks. This is just, I wanted to mention, like the first 3 options that we shared are being deployed at customers, but this is something we are still working on, which is the power-aware scheduling. With this, I would like to run the demo on our turbo rack.
Oh, sorry. There should be somewhere. Sorry about that. Conference. Is there any sound?
Fast velocity of computing evolution has been increasingly raised several big challenges to today's data centers. Decrease of rack density and the utilization of provisioned power. This is a significant contributor to stop a better TCO and service reliability for end users. This video is to introduce an innovative technology called TurboRack. Using distributed battery energy system with smart analytic control. It is very promising to address above-mentioned concerns by leveraging advanced telemetry from Intel Xeon scalable processors. The TurboRack technology is forecast to optimize the efficiency of rack power and performance according to real-time telemetry information. The dashboard collects telemetry metrics, makes real-time analytics, and takes proper control to manage rack power. The intelligent control algorithm is to automatically have rack battery system to supplement extra power over budget line, while still keep overall rack power within budget. We can see most of sporadic power peaks over budget could be shaped without need of expanding rack power capacity or migrating workload out of the rack. In case the rack battery system is not able to afford sustaining power over budget, the power capping is triggered to bring rack power back within safe line. The dashboard provides Redfish interface to integrate with cloud orchestration system for more intelligent job scheduling. Redfish is an open industry standard that specifies RESTful interface for data center management. As the key member of Redfish, Intel has been actively contributing innovations into Redfish. This API has been contributed to Redfish as industry standard. Intel committed to continually improve data center efficiency with innovation. We have been working closely with CSP for better power efficiency and TCO savings through TurboRack technology.
I think we have some time, right? So for questions.
How do you extract the data from, I know that you've mentioned algorithms and software, but is there smart ICs that are giving you the feedback, like sensors and so forth?
Yes, that's correct. But this data that we are collecting is via Node Manager. The question was, how are you collecting the data, right? It's via IPMI or Redfish interface. Did you want to answer anything, Edmund? Edmund is part of my team.
Is it a hard set or is it dynamic in nature?
It's dynamic. So we have two options. One is static. We looked at both static and dynamic. In the static, there could be some performance degradation. So with this customer, we looked at both the options.
The performance, absolutely there is a performance negative impact. However, we can manage that by, because we understand the customer better than the hardware. Then sometimes if we also offer some credit, user may be happy to accept the credit. They understand that sometimes the performance is okay to compromise. And so long as it doesn't hurt their business SLA, then it's good enough. Then that means the hardware, power management, power capping has to be used together with software. Then it can be the best.
And it all depends. With one of the customers we are working with, they are doing static power capping, and it is not impacting their workload performance. So it depends. So that's why we initially do the power profiling and power analysis to figure out what is the right option.
So, Chi from Google.
Yeah.
Curious usage of VB
Admin, you want to offer?
So we also need to consider the constraint from BBU to use the BBU to handle the power because
So he,
because in this case the BBU is still the battery power system in case the power got interruption. So we have two constraints there. One is the SOC, status of capacity. We need to reserve enough remaining capacity to handle the unexpected interruption. In this case, we reserve 85% power capacity for BBU. Another case is a left cycle, left count. Because we use the discharging count to indicate the BBU's health. So we give some constraint is for each day how much percentage for the discharging count to use the BBU to handle the power demand. With this case, we think we can still keep the BBU to be safe. Yeah. Is that answer your
answer
question?
your question?
Yeah, it wasn't a question about safe.
It's what lifetime warranty.
Sorry.
The lifetime. How do you manage the lifetime warranty?
It looks like you say you restrict it to not discharge more than not more than.
Yeah.
It's one of the.
One is for that. Another one is we have the discharging depth for each day. So we don't want to discharging too much for each day.
But I'm curious if you have data to show, with this usage versus without this usage, what is the difference in the BBU lifetime?
Actually, we did observation when we retire some batteries. We found it just a very low percentage of the full recycles of the batteries. That means you are wasting maybe more than 80 or even 90% of your battery lifetime. You can recycle, you can fully cycle your battery more often, and you can take advantage of that discharging.
Any other questions? And you're welcome to reach out to us, and if interested in looking at some of the algorithms we have done, we are open to sharing.
Okay, thank you.